Morning, everyone. Welcome to the seminar series of IvS. Today we have Pablo Huijse. He comes originally from Chile, where he did basically everything in terms of his career. He got his PhD in 2014 in electrical engineering, I believe, and then he continued as a postdoc and became a professor in computer science there. But then, as he says, he became crazy and decided to move to Belgium. I don't think it's so crazy, actually. So it's nice. It's very nice having you here, Pablo. And so currently he is a senior postdoc in Connie's team with specialization in deep learning in astronomy at the moment. So Pablo often says that he is not an astronomer. It's a bit hard to believe when you talk to him. So I suggest you guys enjoy the story by Pablo today about deep learning in observational astronomy. Story told by a non-astronomer who is actually, in my opinion, who knows more about astronomy than some of the astronomers I know. So, Pablo, the floor is yours.
Oh, wow, thanks. Well, it's not crazy, but unorthodox, maybe. That's the correct word. Yeah. And you forgot to mention that it was because I was following my wife. That's also important. Okay, so, well, thank you very much for being here. Let's start with the contents of this presentation. This is the Venn diagram of this seminar. So we will have some theory on neural networks, assuming, that you know a bit of linear algebra, and that's it, perhaps some notions of optimization, but nothing about neural networks. So that I wanted to be, for the broad audience. Then, of course, with examples using astronomical time series and images. That said, I don't want to shoo away people that does simulations, for example, because most of the architectures that I will present can also be used in that context. But the examples are using, as I said, real data. And then, of course, the most important is the neural network's wisdom or tricks of the trade. All the pitfalls that you can avoid, like tips, I'll try to highlight them as we go. So let's start with the beginning. Well, not the beginning of the universe, with an artificial neuron. So I have here this nice schematic of what an artificial neuron is, along with its biological inspiration. You see there is some resemblance. Well, the equation also, if you prefer equations. So basically you have inputs. These are your data, which are multiplied by these coefficients. They call them synaptic weight. Then they are added, and then you apply in what in neural network jargon is called the activation function. So the original one was like this, just a step function, and then you get the output. So what this model what is it doing? So you see, like if we think it geometrically, this is just a linear regressor times a nonlinear step. So this is basically a line or a plane, if we are thinking in more dimensions, that splits the space in two. So this is a binary classification model, very simple. And it can only do like linear splittings, of course. So this was from look at these names, these old names that they use, the perceptron. What a nice name. We don't have those nice names now. So the perceptron we're talking about the 60s. So let's skip some 20 years to the creation of the backpropagation algorithm, which allows to train not one neuron, but a stack of neurons. So now we can have models like this. So you have the input, you have 3 neurons in what is called now a hidden layer. You can have many of those hidden layers. This can be also as wide as you want. And then you have the output layer, which connects to your target. So this is still classification, so we are still trying to separate the data. In this case, I'm showing this. You have this data that has so the crosses and the circles. They are clearly not possible to separate those with a line. It's a non-linear problem. And what I'm trying to show here with this animation, so you see this is the what you see in the output, and this is what you see in these individual neurons. So you see, so each individual neuron is still a plane, is still a line, but the one after those can combine them to form something that is not a line anymore, right? So this is the multi-layer perceptron, 1974, and perhaps this is inspired by, I will share the presentation later in the Slack so you can click on the links. This is inspired on this. So this is the TensorFlow playground where you can do some nice tests to get a feeling of what happens when you change the amount of neurons and so on. So for example, one hidden layer with 3 neurons with the same problem that we are looking here. We train it, we get the result I was showing. Of course, if we remove one neuron, so now we have only 2 lines to combine. Of course, we cannot split this anymore. And if we add a lot more, not layers, but neurons, it's only 8 is the maximum. So you see now it's like a circle, so it starts following the shape of the data better, right? So that's the width, the effect of the width. Similar effect you can get by just stacking more layers. It's also interesting to see what happens, for example, if you change the activation function. So this is a different activation function. We will talk about this later. You see, the geometry of the solution is very different, right? So let's leave that at that and go back to this. Right. Okay, so we saw a bit of the influence of the width, a bit of the influence of the activation function. Some detail here. So you see now we are not using the step anymore. We are using this called the sigmoidal activation, which is kind of a continuous version of the step. Why? Because we need to take derivatives. So the question that follows is, how do we train this? How do we get these nice planes that separate the data? So this is basically an optimization problem. So you have to define a loss function or a cost that you want to minimize. In classification, especially in the case where you have 2 classes, you use something like this. This is called the cross-entropy loss. I don't think there is much more math, after this, so sorry about that, but so you see this cross-entropy loss. So most of the losses that are used to train neural networks, they just come from statistics. So this comes from assuming a likelihood of the output being Bernoulli, like for a binary classification problem. Of course, it makes sense. That's how you get to this. And then how do you train that? Basically, you do gradient descent. Most of the modern neural networks are still using first-order derivatives to update the parameters. And what I wanted to show here, so this is just to explain a bit about the backpropagation method. So backpropagation is just applying the gradient descent method to all the parameters in the network. So you need to apply the chain rule of the derivative. So that's basically it. It's chain rule plus gradient descent. So when you update parameters in the outer layer, you have something like this. And when you have parameters in the next layer, the following layer, the hidden layer, it's something like this. And if you have more and more and more, you start multiplying more and more and more terms, right? So that relates to deep learning, which I will explain soon. Okay, so you do gradient descent. So in practice, you let your model do these iterations step by step. So how do you know if the model went well or wrong? So, well, this here is just like in general in machine learning, your objective is to have your model generalize to data that it has not seen, right? If it just memorizes what you give, then it's not very useful. So typically, you will split your data into a training partition that you use to fit the parameters, a validation partition that you use to tune the little knobs that the neural network has, the hyperparameters, and then a final partition that you don't touch until the end, which is where you measure generalization, the actual performance of the model. So one very good practice is that you train, and in each epoch you log all your losses and all your metrics. For example, if you're doing classification, you can log accuracy. At a minimum, you log the losses. So in each step, you fit the parameters using the gradient descent after selecting a learning step, which is this eta. So you fit the parameters, then you evaluate on the validation, and you have then these curves. So this one, you see, training loss is lower than validation loss, which is typical, but they are both going down still, so there is no convergence yet, so let it cook, basically. That's how you read this. This one, something happened. You see, they were together at the beginning, and then the validation loss went up. So this is overcooked, I mean, overfitted. The model memorized the training data too well, and it's not generalizing correctly. And this one is my favorite. This is basically that you forgot to update the parameters or something. There is a bug. So if you see this, it's not learning at all. Maybe your learning rate is too small, but typically you forgot to connect something. So you have to go find the bug. So as I said, some good practices: always log your losses, always fix your random seed, because this you need to start from some solution. So typically you do a random initialization, and because we are doing gradient descent, depending on where you start, you might arrive to a different place. So fix your seed and test many, not just one. And also it's good that each epoch you save the model, the parameters of the model, the one that gets the minimum validation, and the last, you never know, perhaps your computer crashes and you want to restart the training, so it's good to save the last. And some common training issues, if the loss diverged, like this, for example, well, this is one kind of divergence, but it's only on validation. But if the training loss diverge, that probably means that your learning rate is too high, so the training is unstable, right? You can also have exploding gradients that would look like spikes in these curves. Typically, that means that the data is not in the correct scale of the model. These are sensitive to the normalization to the scaling of the data. You can also have vanishing gradients. That means that your model is basically not updating itself. And this is typically occurs when you have too many layers. It's a consequence of this. Too many layers means too many terms, and many small numbers multiplied can get to 0 sometimes. So you will have useless layers. Overfitting. This is, of course, a very important topic in machine learning in general, but it's perhaps even more important in neural networks because they are so flexible, they can overfit very easily. So if you are in this regime, that your model is overfitting very extremely quickly, you could try, of course, the first thing you could try, get more data. It's not always easy, but it's the best thing you can do. You can either get more real data, but there are also tricks. You could synthesize data. For example, if you're training with images, you can, and you don't need and you want the model to be invariant to rotations, you give it rotated versions of the images. That is increasing the training data, and it's also giving you some nice properties to the model. The second, if you can get more data and you can synthesize, you can try decreasing the size of your neural network, removing layers, decreasing the width, for example, the number of neurons. And lastly, of course, you can also, as in many other methods in machine learning and statistics, you can add some regularization, like, for example, penalize the smoothness of the solution. That's also possible. Okay, so what can I do with neural networks? Well, there are many tasks that you can use them. Here I'm just summarizing the ones that I will show in the presentation. So you have the left side is supervised tasks. So you have data and you have a target, right? So that's the difference between this and the unsupervised, when there is no target or the data itself is the target. So in the supervised, you can have, for example, classification. You want to partition the space, or you can have regression. You just want to map one variable to another. So here the difference is just that the target is categorical, and here the target is continuous. but the architectures are mostly the same. I mean, you can use the architectures for classification, also for regression. You just change the last layer, the output. Unsupervised is a bit different. So you can have, for example, dimensionality reduction. This is similar to PCA, for example. You have your data, can be very complex, like images, and you reduce them to a couple of numbers, right? So we will see this architecture. You can also do data synthesis, like generation, right? So those are two unsupervised tasks. So deep learning, what is deep learning? Some people say it's many layers, plus big data, plus hot graphical processing units. Nice to have them in winter, actually. And actually, I can't say no to that. But there is a bit more nuance to this. So it's not only many layers. It's like a change in paradigm between what traditional machine learning is or was. Well, it's still there, of course, and what deep learning attempts. So in the traditional machine learning, you have your data, you compute some features. For example, you fit polynomials, you fit Fourier series, you fit some random walk model or something, and then you use the coefficients from those models to train a classifier. That's the traditional approach. The deep learning approach changes the architecture so the model can do feature extraction and the high-level task, for example, classification, at the same time. That would be the main difference. And of course, this does not replace this. If you know that polynomials are the best for your problem, just go with this approach. But in other problems, like for example, when you are working with images, imagine a face detector, cooking features to detect faces is very hard, so it's better to learn them automatically. So in that case, deep learning works better. Deep details. I already said that when you stack too many layers, you start getting vanishing gradients. So the model does not learn properly. So how can these guys do like 30 layers or 50 or 100 or having billion parameters like ChatGPT? Well, perhaps one of the first, let's say, key additions to get this is all about letting the gradients flow. So in 2010, people start using this activation function instead of the typical, the sigmoidal. You see this rectified linear unit, or ReLU. It has a half nonlinear and half linear. So in the linear part, the derivative is 1. The derivative of the dx over dx is 1. So you have a linear part where the gradients can flow easily, and a nonlinear part where, well, it's 0. Then you have this approach this is the famous residual architecture, where you have these skip connections. So the gradients can flow more easily back to the input. So these are methodological improvements that really allow the training of very deep neural networks. Well, there is also, of course, the difference between the architectures, which we will explain now. So last question before going to architectures and some astronomical problems is how do I implement them? There are many libraries nowadays. So if you like Python, you have PyTorch, TensorFlow, JAX, and Keras. Just choose your big tech corp. So it's either Facebook or Google again. You have to sign the pact with the devil. If you want to start, I would suggest Keras because it's a higher level kind of library with a lot of functionality already there. So if you don't want to do like a very customized loss function or very customized neural network, you can do Keras. And Keras is actually use these 3 as a backend. So you can you can change JAX, PyTorch, or TensorFlow as backend and continue using Keras. Well, in any case, if you like Java, you have this DL4J. I don't know if I've been forced to work with that. And if you like Julia, there is also Flux, which looks really nice. There are libraries for Rust and so on. So what these have in common is the ability to have this container, this array that can be moved from CPU memory to GPU memory and allows GPU computation. So that's one of the keys. The second key is that all of these libraries, and the very, let's say, the base, they are just machines to compute derivatives. So that's the main ingredient that you need, GPU and autograph functionality. And well, this is an example, the very simple network that I showed before, only one hidden layer and one output layer. This is how it looks in PyTorch, the training. So you define a model, in this case it's a sequence of layers, then you define an optimizer, some derivative of stochastic gradient descent, and then you do your mantra for each epoch in how many epochs you want. You do predictions, you compute the loss, you compute the gradients, and then you update the parameters. Sounds very easy, right? Maybe you don't need me. This is so easy. Of course, the important part is how do you design this? So there is much more to it. So let's go to architectures. So the first one that started popularizing deep learning was this called the convolutional neural network. So most people associate this to images. But basically, I mean, well, images, of course, there are images in astronomy, but I would like to emphasize that this is not only for images, it's for data that is organized like a grid, like a regular grid. So you can have a 1D, 2D, 3D, 4D, whatever type of grid. So that's the first important detail of these convolutional neural networks. So images are grids, 2D, but you can have, if you have a regularly sampled time series, not typically the case in astronomy, but if it's typical in audio, for example, that's a 1D grid. A video is a 3D grid, and so on. So that's first detail. And the second detail is that they provide this assumption. They are translation invariant. What does it mean? So you see these layers, the neurons are like little filters that they convolve with the grid. So they move on the grid, right? And they detect patterns. It doesn't matter where they are. So the cat can be on the right or on the left. But for the convolutional neural network, it's the same, right? So that means that is what means being translation invariant. So a fully connected neural network, like the ones before, where you put every pixel as an input, you move the cat, and the prediction is totally different. But in the convolutional one, it is not. And then again, look at these names. Neocognitron. Well, most people know about the LeNet 5 from Jan LeCun. I mean, he made this very famous, but the actual inventor of this is a Japanese, Fukushima. And I mean, he totally beats him on the name. Okay, some more details about convolutional neural networks. So typically, you have a stacks of convolutions, like each, layers of convolutional filters. The filters are usually very small, for example, 3 by 3 pixels. That means that the first layers only see a small part of the image, but then subsequent layers are seeing larger and larger parts, right? So this is the result of how we are composing. So you don't need to, I mean, if you want to find something like a head of the cat and use a lot of space in the image, you don't need to put a filter that is the size of the head of the cat. You just do small filters and compose. Because in that way, you can exploit a bit better. For example, this is what's shown in the Saylor and Fergus paper, a very important paper. So if you do like this, like composition of very small kernels, the ones near the input, they learn like very simple stuff that is everywhere, like lines, gradients, some textures. And then the ones on the top, they learn like this Cocker Spaniel filter or whatever that is very, high level compared to this. And this is composing this. So it's like building blocks. Astronomy, okay, something more fun for you. So I would say that the convolutional neural network, the first one used in astronomy, I think it was this, the Dilleman 2015, where he used this galaxy zoo data. So he wanted to solve this galaxy morphology classification. So it's elliptical, spiral, irregular, whatever. And then after that, we get inspired by that into trying to solve this problem of real transient versus artifact in images from the dark energy camera. What these architectures share, they are both convolutional architectures, you see, so each of these is a convolutional layer. But we wanted, I mean, in both cases, you see there is not only translation invariant, which is built up in the architecture, there is also like a forced rotation, flip kind of invariance. Because in this case, of course, the galaxies can be rotated wherever they want, right? So it makes sense to have your architecture being rotation invariant and also flipped. So you can cook that into the architecture like this. So you have the same, so this is the convolutional layers. You apply them to the original image and to rotated versions of the image. So that's a way to embed the rotation invariant. And this is how you start, you add like your assumptions, your inductive bias in the model. So 2 examples, a more modern example. So this is something that we developed for the ALeRCE broker. That I will talk about that in the end. But basically, it's as the one before. So now with more classes. So you have images from ZTF. You have the science, the reference, and the difference image. So the idea is that if there is something in the difference image, an alert is produced, and we want to know what this alert, what it corresponds to. Maybe it's a AGN or a supernovae, or maybe it's just a variable star that is pulsating or something, an asteroid, and perhaps the favorite one, crap, just crap. There's a lot of crap, always. So this is the same idea. You train with now with the tuple of 3, we call them stamps. Sounds cute. They are very little, like 21 by 21. So we have these stamps from the alerts. You rotate them, you process them with the convolutions, and then you classify with a fully connected layer with the addition of some metadata. So this is the stamp classifier. CNNs have also been applied for light curves, but the performance have never been so nice, actually. It's very hard to beat like a regular random forest with features. And I would say that it's because light curves are not, not a good match for 1D convolutions, especially in this case, where you have very irregularly sampled time series. So what these guys did, they attempt to transform the light curve into an image to use a 2D convolutional network. So they get the light curve, they compute this histogram of the m delta magnitude and delta time, and then you have something that looks like this. But the performance was not so good, actually. But it's part of the history. The same with this. So in this case, they were just feeding the delta times and the delta magnitudes. So it's nice, it was novel, but not better than a regular classifier. And as I was trying to say, convolutions assume a regular grid, and this is clearly not a regular grid. So it's not a good bias, not a good inductive bias for this. Perhaps other time series that are more regular, like tests, where convolutional 1D convolution can work nicely. Autoencoders, so another architecture. So you have, this is as unsupervised learning, so there is no target variable, or more precisely, the data is the target. So data enters here, outputs something there, and the task of the autoencoder is to match what enters and what is here, what is predicted, right? They have this funny Diabolo-looking architecture where you first reduce the dimensionality, so this is doing compression, and then you put it back to how it was in the beginning. You return to the original dimensionality so that this can be subtracted and error can be minimized. And the amount of neurons in this code, in this bottleneck, of course, that's what controls how much you compress. So this is like lossy compression, right? Example. So this is an autoencoder that it's making a 2-dimensional projection. So just 2 latent variables with, again, stamps. These are 21 by 21 different image stamps, around 20 million objects the Chase survey was spitting. So anything that had a bigger than 5 sigma in the difference, boom, it's a stamp. So what are these? That was the first question. Can we characterize everything that we are looking? And that's what I attempted to do here. So you have your input. This is the prediction. You have the encoder and decoder. You have these two numbers. And this is showing how these two numbers, for the 20 million, of course, this is a histogram, because plotting 20 million points is a bit crazy. But you can see how it evolves with the training. So it starts somewhere in a random place, and then it's accommodating in this space of latent variables. And this is from the latent space, these two numbers go back to the image to reconstruct. So you can see all the shapes that are within this set. Here is a bit more detail. So you have all sorts of crabs, as I said, our favorite class, bad subtractions. I mean, the science and the reference were not correctly aligned, and you get these fake alerts. You have these big blobs, which are also not good. I don't remember exactly why they were not good, but I think it was a very bright pixel that then starts like going like this. But the good stuff is here. I mean, not too small, not too large. This is the good stuff. Well, I mean, these guys wanted supernovae, but these were mostly asteroids. So, close enough. I mean, I guess one of these was a supernovae. Of course, with only two, I mean, with only one difference, it's a bit difficult to discriminate. But if you add more differences, then of course it will get you can do that. Another architecture, another bias for our neural network. So we have recurrent neural networks. So these basically have a sort of memory, right? So each prediction is made with the current input. So you can imagine a time series. Each observation in the time series is one of these. And each prediction is made with the memory and with the new input, right? So this is made for sequences, to learn temporal dependencies. And this, in the 2000s, they were used in practice. Before this, it was very difficult to train them. But with the long, short-term memory, which added all these complicated gates that control what enters the memory and what gets out of the memory, these were used in practice to solve actual problems. Example, this is a recurrent autoencoder that was made for folded light curves. So it's two papers, 2018 and 2020. So you see light curve, you get the dominant period, you fold them, so you are already assuming that these are periodic, and you have one stack. So this is the encoder. You have one stack of recurrent layers, a second stack of recurrent layers, and here enters magnitude, folded magnitude, and also the phase. Then to the second layer, and the last of these memory states, it goes to the decoder. So you just clone this n times, and you append the delta phase, and from that you attempt to reconstruct. So these are reconstructed magnitudes. And the objective is, as a typical autoencoder, you try to match this and this, which, so yeah, that's basically it. This also an example, it might be useful for you. It's a project we work in 2021. So this what I call the half autoencoder. So in all the examples before, we have a fully learnable encoder and decoder, but perhaps you don't want that. You have a model, a generative model that has some parameters, because, well, one important thing here is that these latent variables that you learn, they are kind of hard to interpret. They can be whatever, right? But sometimes you want them to have some meaning. So one way to do that is that you force the decoder to be a model that you know, right? That has some parameters. This is a very simple phenomenological model of this type 1a supernovae. So you start with the data. You have an encoder, which is a neural network. In this case, you see very irregular light curve, so that's why we didn't do convolutions with the recurrent neural network that predicts the parameters of this model. So that's why I say it's a half autoencoder. The idea was use this as a very quick replacement, because of course you can, if you have this model, you can do MCMC, but the problem is that you get 1 million supernovas every night. It's a bit expensive to do MCMC, and you want to take fast decisions for follow-up, for example. So this is like you take a lot of time to train, but then the inference is very quick. And predictions are, well, not so bad, I would say. Not too different, except in this one. So this is an example I thought that perhaps it's useful for you in a more general sense. Okay, so I think this is the last of the examples, yes. We still are lacking in the naming department, so it's a bit boring. We have to think a bit more about that, perhaps. So this is a project that I've been working here in the KU Leuven with Joris, attempting to digest the Gaia data release 3 in preparation for the data release 4. So just to give a bit of context, we know that in data release 3, they published classifications using supervised methods, like particularly ensembles of decision trees. So there is this, need or perhaps curiosity of trying an unsupervised approach. Can we classify without using the labels? They themselves, they don't trust the labels. So perhaps we shouldn't trust them either. So can we get what are the difference between the unsupervised and supervised? That's kind of questions that we would like to answer. So in this case, I'm using 2 data products from Gaia. One is the G-band time series, and the other is the XP spectra. So this is blue one and the red one. So this is low resolution spectra. So the G-band time series, it gets folded, and then we build this image-like DMDT, similar to what I showed before. So this basically shows at what time scale is the object, the variability of the object more stronger. So is it a low time scale object, a high time scale object? That's what is reflected here. So each of these are compressed with an autoencoder, a different autoencoder, using its own architecture and cost function, around 4.2 million sources that were already classified as variable because data release 3 only published. Most of the sources are variable only. So the end is we have 15 numbers that describe these 4.2 million sources. So what do they look like? So for example, this is what you have some of the variability classes: delta scuti, quasi-stellar object, eclipsing binaries, ALeRCE, and LPVs. So you see some of them, for example, these 3, they don't differ much in the spectra department, but they do have very different folded light curves and very different time scales. ALeRCE also have a very different, very particular shape, while eclipsing binaries, this is expected, and LPVs are very red. So, so this is the result of decompressing the sources belonging to these classes, just to see what did the model learn about these classes in general. Then we also attempt to do like a stronger compression from 15D to 2D, just because looking at 15 dimensions is a bit difficult for a human. So in this 2D projection of the 15D latent variables, you still see nice separation of the variability classes, even though, as I said, we used data from variable stars, but we didn't pass the label to the model. The model doesn't know that these are eclipsing binaries, and these are ALeRCE, and these are LPV. So this is very nice. And of course, we are in the process of writing a freaking paper. Yes, just again to show that you can separate these classes very nicely in this latent space. And these are performance curves used in classification. The only thing you need to know is that being in the top left is good, and using all the modalities, meaning the combination of spectra, folded, and DMDT is always the best choice. But for some variability classes, there are differences in which of these individual modalities are more important. For example, eclipsing binaries, the folded is very important. The spectra, kind of useless, because, well, there is a lot of overlap of the eclipsing binaries in the spectra with the other classes. But in the QSO department, it's the opposite. Like the folded is useless, because these are mainly non-periodic. But the spectra is very important, and the DMDT is also very important. So these are some of the results we want to show. So it's just perhaps, yes, last two slides. So this is a project I wanted to highlight, something I was working on before coming here. So this is a astronomical broker. A broker, what's a strange term, it's used in economics, no? Like the middleman. But this is something that is being popularized by this, for example, ZTF, or the large synoptic survey from the Vera Rubin. They will produce this stream of alerts, and they are calling for systems to connect to those pipelines, ingest the alerts, classify, and produce some outputs that are useful for the community. So this is a nice project in the sense that this is a lot of a combination of very deep astronomical knowledge, models, and a lot of engineering too, to make this work. So nowadays it's classifying ZTF alerts. There are some links there. Maybe I can show one, not this. So this is the Supernova Hunter. That's a good name, no? So you have the supernovas from the last 72 hours. Look at this, so nice. The template, the science, and the little dot. And then if you click on this, you go to other services. Let's see if this works. You can see the time series. And this works also because we were classifying not only transient, also periodic variables and other stochastic variables. You can select them, download them, cross-match them, and so on. So that's, if you totally don't want to train your own model, your own neural network, you can go here and use this. I mean, if you use ZTF data, of course, or LSST. So closing remarks. We talked a lot of architectures, and I was mentioning this term is inductive bias. So what does it mean? Inductive bias, just as a summary, is all the assumptions that we are putting in our model. So some of them are explicit. For example, in Bayesian modeling, you put a prior on the parameter. It can't go above or below this range. That's an explicit assumption. But there are also implicit assumptions that arise from your architecture. So this is important. Typically, people say, this is an image problem, I will use convolution. But my suggestion is that you think not only not only like that, but also in what kind of assumptions you want to put in the model. Perhaps you have something that is like a grid, but you don't need the translation invariant, or you know that it can be, it will not be beneficial. So you better not use convolutions. That's what I mean. So if you have, you want translation invariance, you want dependence on the past, you have a set, and they can have all sorts of relations. You can use attention, something I didn't talk about, but perhaps, I don't know, next seminar, next year, something like that. You can also do, like, cook invariances with this technique, for example, of adding the rotations, or adding, for example, if you want the model to be robust to noise, in an autoencoder, you can add noise to the input, but attempt to predict the clean data. So that's, you make it invariant to noise. Of course, it's invariant to the noise that you are putting. Is it Gaussian noise or whatever? So that's also something that is interesting. And then finally, after you have decided on the architecture and you have your implementation things to have in mind when you are starting the training procedure, the first suggestion is try to overfit. Use a little bit of data and let your model totally memorize the data. Why? Because that says that your training script is good. If it cannot memorize a very small amount of data, then there might be a bug or a problem, or maybe your assumptions on the here are not correct. So try to overfit first, then reduce the complexity, then do regularization and so on. So these are sensitive to the scales. Don't forget to normalize and scale. Or you either do that or you change how the parameters are initialized. And in terms of optimizers, there are all sorts of adaptive learning rate optimizers like this. This is very popular. So start with this. You can get better results by tuning the learning rate yourself, but I would suggest start with this, then deal with these two, and then go back to comparing different optimizers. And also don't forget that this is gradient descent. This can be a local minima, so you need to try different initializations. And yes, that's it. Thank you.
Thanks, Pablo, for an interesting and educational seminar. Time for questions.
Indeed, thanks for the very educational seminar. I was actually curious with your work on GaiaNet.
Yeah.
So firstly, actually, how is the phase folding happening?
Yes, good that you ask. I can provide more details now. So we get the G1 time series. We compute a LOMS kernel, get the dominant frequency. Then this gets folded with the, you see, twice the dominant frequency. That's why it goes like up and down, up and down. And this architecture perhaps is the most interesting one because it's the most different from the more special, I would say. So this part receives this sequence. This is a recurrent neural network that has it has a small attention component. So just to pick or to learn to reject some of the points that might be outliers. And this part here in the decoder, so this receives the 5 numbers that you get from this one, and then you append the phases, but in polar coordinates. So you append the cosine of the phase, the sine of the phase, and a bit more harmonics actually. So, and you reconstruct from that. So it's the bias here is that, so because this is phase space, this has to be periodic. So that's what I'm trying to encode here. That's the bias I'm trying to encode here. For these two, for example, this one is actually a fully connected network. In the beginning, we thought maybe we could try convolutions. But the thing is that if, for example, let's say you have a spike, and the spike can move in the spectra. If you want to find the spike, no matter where it is, then convolution would be good. But in this case, we want to know where the spike is located. We want to know if it's in 15 or in 20 or 25. So that's why we used fully connected, because there you have the position. You know, it's, I mean, you preserve the order. I mean, after looking at the results, we have seen that some of the details that this network doesn't reconstruct well is actually spikes that are in different parts. So perhaps the best architecture would be a combination of fully connected and convolution. So convolution to find if there is something going up, no matter where it is, and then the fully connected to just learn like the general shape. But I already made Pinky promise that I will not change the model, that I'll write the paper, so, or Joris will keep me. So that's maybe for data release 4. Yes.
If I can just follow up.
Yes.
So actually, then I'm curious, what happens when you have multi-periodicity?
Well, if you have multi-periodicity, this fold will be crap.
Okay.
And
Just to know.
this model can also, you see it outputs like a periodic shape. Yeah. It can also output these error bars. Yeah. So what we see typically when something is not periodic, yeah, so it can't fit well, it will give you a big error bar. Yeah. So the model can still kind of find where the folding doesn't go correctly. But yes, I mean, perhaps we could, for example, instead of doing folded with the dominant, we can add like this can be like 3 stacks that go in parallel, the dominant, the second best, the third best, something like that. But again, I can't do any changes. No, no, no. Yes, data release 4. Data release 4. Yes.
Thank you.
More questions? Yep.
Hi, thank you for the talk. I have two questions, one about this. So I guess if you have hybrid classes, the discriminating part would be the DMDT. Is it the right intuition?
So this is the only one. So this doesn't have information of the periodicity, it's just the shape, right? So this cannot discriminate if in terms of frequency. But this one can, I mean, it could, but it depends on the time scales, because you see, we are using these very particular time scales because Gaia has this burst in sampling. So we have data in this very small cadence. And then we have huge gaps. So we can't, this is actually like a very low resolution way to discriminate between the timescales. So if you are lucky and one periodicity falls here and the other here or here, then you could separate them. But if that's not the case, it's a bit more difficult. Actually, so we have some labels of Gamma Dor and Delta Scuti. If we go back here, so this is, so in Gaia DR3, they actually merge Delta Scuti and Gamma Dor. According to them, they cannot be separated. It's a bit of a stretch, maybe. But actually, the Delta Scutis are more to the right, and the Gamma Dor are more to the left. But the hybrids are everywhere. So that could mean, I mean, perhaps you don't have enough information on the light curve, or perhaps the label that I'm using to color this is not good. That's something that we need to explore. That's part of the analysis of this that we need to do. Yeah.
Can I have a second question as well?
Yeah, sure.
So you showed two papers on CNNs with very bad sampling. Would it
you mean this?
yeah. So would it help if you phase fold? Would it work better then?
I mean, you see, so after these guys failed, you start seeing these papers not using convolutions anymore, but folding. Because in the phase space, it's much more regular. And actually, so in this one, they used convolutional neural networks and compared them to the recurrent neural networks, but after folding and after interpolating. So they make them regular, right? When, I mean, if it's like this, interpolating is not so bad. But if you have really, I mean, if you have a few points, you have some, I don't know, spurious periodicities or spurious gaps due to sampling, then interpolating, even in the folded light curve, might not be so good. But at least for these were macho and oval light curves. And in that experiment, they found that the CNN, 1D, and recurrent basically achieved the same result on the interpolated folders. Yeah.
Very cool. Thank you.
Any more questions?
Hello. So in the Gaia net thing you showed, the middle one with the face folded one, if the middle Z2 is just, as I understood, it was 5 numbers.
Yes.
How do you in the end get out an error margin on it? Because it's those 5 numbers that then get remade into an image, and there are no like variation on those 5 numbers, right? Or
can you repeat the question? So yes, these are 5 numbers. So this is encoded into 5 numbers, and then this expand the dimension back to the original.
Yeah, so how I understand them is that the right side is just a very complex matrix multiplication to get back to an image. Maybe
well,
oversimplifying greatly.
Yes, but it's close enough. I mean, fully connected neural networks are just matrix multiplications. But when you start doing recurrences and stuff like that, it's a bit more complicated.
I think that's the better way to ask it. Yeah.
Okay, yes. It's variational autoencoder is something that I didn't mention because I didn't want to overcomplicate the talk. So this is not as just the regular autoencoder is actually, it's called variational autoencoder, where each of these Z is not a number, but a mean and a standard deviation.
Okay, there we go. Yeah.
So it's a probabilistic model.
Okay.
And the output is also a probabilistic model. So it's closer, it's something, where was this? So it's a mixture between this and this. So you have a distribution for Z, distribution for the reconstruction, and that's how you get error bars in here and in here, right? There are more tricks, of course, because you see the light curves, so they all have different number of points. So you reconstruct this, but you only test the performance on the samples that you have, which are different for every light curve. So that's also something that you need to take into account when working with the variable length and very irregular data. Yes.
Thank you.
All right, we are at the hour. Let's thank Pablo again. Thanks for coming and see you next week.